So as we've seen already in this class, taking integrals is a really important skill and something that we do a lot and that we need to be able to do to find properties of quantum mechanical systems. And when we integrate, so if, say, we're integrating the particle in a box wave function, it's important that we always include this differential element, this dx. And this may seem like a formality, but for example, in 3 dimensions, if we do this in Cartesian coordinates, our differential element becomes now a differential volume element, dx, dy, dz. You can kind of think of this as a little cube. So this is now a differential volume element. Okay. For spherical coordinates, this differential volume element isn't simply just dr, d theta, d phi. That would be too convenient. So in spherical coordinates, our differential volume element is still, the equivalent of dx, dy, dz, but we have to use the definitions of x, y, and z in terms of r, theta, and phi to get this in the correct terms. So dx becomes r sine theta d phi. Y becomes r d theta, and we end up with a dr as well. And so if we combine all this, the differential volume element for spherical coordinates is r squared sine theta dr d theta d phi. So when we integrate in spherical coordinates, we always have this extra term of r squared sine theta that shows up because it's part of the differential volume element. So even if you're integrating nothing, right, even if you're integrating over a constant, the r squared sine theta will always be part of this. So let's look at an example of how we do an integral in spherical coordinates. So we'll look at the wave function of a 1s orbital. So this is something that we'll get to in chapter 6, but we'll just introduce this wave function. Psi is equal to 1 over the square root of pi, 1 over a naught to the 3/2, e to the minus r over a naught. A naught here is the Bohr radius that we've seen before. So one thing we'll see is this particular function has no dependence on either of our angles. It doesn't depend on theta or phi. And this is a property of s orbitals that you're familiar with because they're spherically symmetric, right? It doesn't matter which way the angle points. You get the same value no matter where you go. And so that's what makes s orbitals the shape that they are. So if we want to integrate this, let's say we want to look at is this wave function normalized? We need to do an integral over all space of our psi star psi. And so let's put in specific values here. So we have to integrate over all 3 variables that we have, and we have to get the right ranges here. So for r, we go from 0 to infinity. For theta, we go from 0 to pi. And for phi, we go from 0 to 2 pi. And then we have so because this isn't a complex wave function, psi star and psi are the same, so we'll just take the square. So we have 1 over square root of pi, 1 over a naught to the 3/2 power, e to the minus r over a naught squared. And then for our differential element here, we always have r squared sine theta, and then we have dr, d theta, d phi. Okay, and so what we can do is separate this out into each of the variables, separate into the parts that depend on each variable. So we will end up with kind of 3 one-dimensional integrals, and then we multiply them all together. So we'll collect all of this stuff out here, right? That doesn't depend on any variables. So we'll just get that out. We have 1 over pi and 1 over a naught cubed. Okay, and so then we'll have our r part, and let me just do these in different colors to make this a little bit easier to follow. So the 0 to infinity will have e to the minus r 2r over a naught. And so the 2 comes from the squared, dr. And we also need our r squared. So this r squared here will be part of this as well. Okay, so then we'll switch to blue. And we have the integral from 0 to pi. And this sine theta needs to come there. Sine theta d theta. And then there is no explicit phi dependence, so we'll end up with 0 to 2 pi of just d phi by itself. And we can solve each of these separately. So for the first one, we'll use an integral table. And I'll just give you the final answer, but this is something you can look up in an integral table. We end up with 2 factorial over, let me read my notes here, 2 over a naught cubed. All right. The integral of sine theta is negative cosine theta, and we evaluate that from 0 to pi. And this one's easy. Whoops, I thought I switched colors. This will just be 2 pi. Nothing fancy here, right? We're just integrating 1. And so when we evaluate these 3 integrals, we end up with, so we have our constants out front. All right, and so once we evaluate this, we'll get 4 over 8 times a naught cubed. We end up with 0 plus 1, and we end up with 2 pi. Okay, so our a naught cubes cancel, our pi cancels here. We get 2 times 4 cancels here, and overall we get 1 as we should for a normalized wave function. All right, and so that just kind of walks you through an example of the process of how we actually do one of these integrals where we're looking at spherical coordinates.